Hello and welcome to your Algebra 2 Lesson 5.7, Apply the Fundamental Theorem of Algebra. So the objective today is going to be that you will classify the zeros of polynomial functions. All right, a little background. The equation x cubed minus 5x squared minus 8x plus 48 equals 0 becomes x plus 3 times x minus 4 squared equals 0 when factored. It has two distinct solutions, -3 and 4. Because the factor x minus 4 occurs twice, 4 is considered a repeated solution. Specifically, it is called a double solution. So, with 4 counted twice, this third-degree equation has 3 solutions. This can be generalized into the fundamental theorem of algebra. Thank you, Carl Gauss. The fundamental theorem of algebra. The theorem states, if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. So first of all, it was established there's got to be at least one solution, real or imaginary, if n is greater than 0. Well, now there's a corollary based on this theorem. If f of x is a polynomial of degree n, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, each solution repeated 3 times is counted as 3 solutions, and so on. So how many solutions does the equation x cubed plus 5x squared plus 4x plus 20 equals 0 have? Well, you simply look and see what the degree of the polynomial is, and that'll tell you how many solutions. So since this is a third-degree polynomial, there are 3 solutions. Okay, so in other words, because x cubed plus 5x squared plus 4x plus 20 equals 0 is a polynomial equation of degree 3, it has 3 solutions. The solutions are -5, -2i, and +2i. The question doesn't ask for that, but it's easy to find the answers, and so there they are. How many zeros does the function f of x equals x to the 4th minus 8x cubed plus 18x squared minus 27 have? Well, zeros of the function are simply the solutions when we get when we set the polynomial equal to 0. So again, we can still just look at the degree. Because f of x equals x to the 4th minus 8x cubed plus 18x squared minus 27 is a polynomial function of degree 4, it has 4 zeros, and those zeros are, by the way, -1, 3, 3, and 3. On a problem like this, again, you don't have to provide the zeros. Just tell, how many zeros there are. Now, on this one, you're asked to find all the zeros. So we want to find all zeros of f of x equals x to the 5th minus 4x to the 4th plus 4x cubed plus 10x squared minus 13x minus 14. So, just like I told y'all in the last lesson, anytime you have a polynomial like that and you're asked to find the zeros and you can't factor it, you need to think immediately P over Q. You need to find all your possible rational zeros, and then you can work from there. So we're going to find the rational, actually it's the possible rational zeros of f, and then we'll actually find the rational ones. Because f is a polynomial function of degree 5, it has 5 zeros. The possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. Because our values for p come from that constant of -14. And then our q is the factors of 1, so just plus or minus 1. And so when we do our p's over q's, that's the list we come up with. Well, that's nice. Let's go ahead and look at a graphing calculator to see which values might work. If this were on a non-calculator part of a test or in a situation where you couldn't use a calculator, just start with 1, try 1, and then move to -1, 2, -2, and work through your list until you find one that gives you a remainder of 0 when you do synthetic division. But it doesn't hurt us. We can to use our graphing calculator. So let's go ahead. Clear out, do dot B to clear out your scratch pad, and then for the graph, go ahead and define f1 with your polynomial function there. Go ahead and enter that. Now, if you'll notice, I adjusted the window where for the x min it's -5 and x max is 5, and still and did -10 to 10 for my y min and y max. And so if you want to make your picture look just like mine, make sure you look and notice what window I have. And you can tell that by just looking, you know, on the x-axis, and that'll give you the x min and max, and on the y-axis, and that'll give you the y min and max. All right, so looking at that, here's -1 and here's 2. Now, because right here, right around -1, it looks like a little parabola, okay, right here, that is an indication that -1 is a double zero. It's going to look like a little quadratic there because it's actually from x plus 1 squared that we would generate the 0 of -1. Over here, for 2, see how the function just passes through like a line there? Well, just right there, not the whole thing, obviously the whole thing is curved, but right there, right in the neighborhood of where it crosses 2, it looks like a line, and that tells us that it is a linear factor that gives us the 2. So let's check with synthetic division, because it could be an irrational number just really close to it, but let's go ahead and check. So let's start with -1. So we're going to go ahead and send -1 through the original polynomial and try to divide and see if it works, and that'll give us if it does, it'll give us the quotient that has x plus 1 factored out of it. So here's our original values from our original polynomial. So 1, -4, 4, 10, -13, -14. Okay, and here's our -1. So we bring down the 1, and we do 1 times -1 is -1, -4 plus -1 is -5, times -1 is 5, 4 plus 5 is 9, times -1 is -9, plus 10 is 1, times -1 is -1, -13 plus -1 is -14, times -1 is +14, -14 plus 14 is 0. So we've done a couple of things here. One is we have affirmed that -1 is at least a single 0 of our function. And that means that x plus 1 is a factor of f of x, and then these values down here give us our quotient. So the other big factor of f of x. So we could write f of x equals x plus 1 times x to the 4th minus 5x cubed plus 9x squared plus 1x, or x minus 14. Okay? Now, what we want to do is, since we suspect -1 is a double zero, we want to go ahead and do synthetic division again, but on the quotient, or what's called the depressed polynomial. So we're going to send that -1 back through, but we're going to use these values, or quotient values, in our top line. Okay, so we bring down the 1 times -1 is -1, -5 plus -1 is -6, times -1 is +6, add that to 9 to get 15, times -1 is -15, 1 plus -15 is -14, times -1 is +14, and we get 0. So we have factored an x plus 1, another x plus 1, and we're left with the quotient x squared. Actually, this is 4th degree, so this is 3rd degree. X cubed minus 6x squared plus 15x minus 14. So we're going to take 2 and we're going to put it through this quotient. Okay? Because we're trying to get down to a quadratic. So we want to keep using these depressed or quotient polynomials when we do our new synthetic division. So we recopy the quotient row now as our top row, and we're sending 2 through. So we've got 2, and then 1, -6, 15, -14. So we bring down the 1, and then we multiply by 2 to get 2. -6 plus 2 is -4, times 2 is -8, 15 plus -8 is 7, times 2 is 14, -14 plus 14 is 0. And so here we've got our coefficients of our quadratic, x squared minus 4x plus 7. So if we can factor it, that's great. If not, we'll take the quadratic itself and set it equal to 0 to find our last two zeros. So far we know -1 is a double zero and 2 is a 0. Okay, so our second step is write f of x in factored form, dividing f of x by its known factors x plus 1, x plus 1, and x minus 2 gives a quotient of x squared minus 4x plus 7. Therefore, f of x equals x plus 1 squared times x minus 2 times x squared minus 4x plus 7. Now, we know that if we can factor this, we're going to have two more nice rational zeros. But we can't. This is prime. So we're going to set x squared minus 4x plus 7 equal to 0 and solve, and that will either give us complex zeros or irrational zeros. It'll give us one of those. In this case, it's going to be the complex zeros. So we're going to find the remaining zeros, which happen to be complex, of f. We're going to use the quadratic formula to find the zeros associated with the trinomial factor x squared minus 4x plus 7. So a is 1, b is -4, c is 7. So x equals -b, so 4, plus or minus the square root of b squared minus 4ac. So that's going to be 16 minus 4 times 1 times 7. So that's 16 minus 28, which gives us -12, all over 2 times 1. All right, so we need to simplify this. The very first thing you would do is put your I out. Okay, so that's where the I comes from. And then 12 is 4 times 3. Square root of 12 is 2. So that's how we get 2i square root of 3. Now, to simplify further, we do 4 over 2 and then plus or minus 2i square root of 3 over 2. 4 over 2 reduces down to 2, and then we have our plus or minus. Our 2's cancel in our second term there, and we have I square root of 3. So our two complex zeros are 2 plus I square root of 3 and 2 minus I square root of 3. So here we go. The zeros of f are -1, -1, 2, 2 plus I square root of 3, and 2 minus I square root of 3. And that gives us our 5 zeros. All right, one thing you may have noticed is here, 2 plus I square root of 3, 2 minus I square root of 3, those are conjugates because they're exactly the same, but one with plus and one with minus. And if you think about it, if we're generating imaginary zeros, we're using the quadratic formula, so we're always going to have this plus or minus situation. So imaginary zeros occur in conjugate pairs, and that leads us to the complex conjugates theorem. If f is a polynomial function with real coefficients and a plus bi is an imaginary zero of f, then a minus bi is also a zero of f. The same thing works for irrational numbers, because the only way you're going to come up with irrational real values is if you're using quadratic formula. And again, you're going to have this plus or minus situation. So suppose f is a polynomial function with rational coefficients, and a and b are rational numbers such that the square root of b is irrational. If a plus square root of b is a zero of f, then a minus square root of b is also a zero of f. So knowing one is a conjugate actually tells you that two irrational numbers are conjugate or zeros because the conjugate comes with it. Okay guys, that's it for video 1. I will see you again in just a minute for video 2, and we'll do our last 2 examples.